Okay, we're gonna do the revised simplex now. This is a way of adding some bells and whistles to the simplex code. Optional for your assignment, but it's super helpful to know what's actually happening behind the production code. Every production code is going to do a revised simplex. So we know that the number of simplex iterations is somewhere between, here's our good case, right? ON linear, or worst case analysis, OM choose N. But let's focus on how much work is done at every iteration. That's about the number of iterations, but could we do something that reduces the work per iteration? So which step of algorithm 5A requires the most work? So let's pull that up. Okay, so here's algorithm 5A. This is the basic one you have to code. Choose an initial starting feasible solution. Let's assume we've got that because for your code, like that example, they were all AX less than or equal to B, which is the easiest case to get a basic feasible solution. Just adding your slacks and choosing those. But we know we could solve another, do the two phase and solve that. So let's assume we're now at step one. Step one, we need to construct a simplex and then get our reduced costs. The reduced costs are just inner products or dot products, so that's ON work. We'll come back to this, getting the simplex direction. Step two, we're just checking if we're optimal. So we're just looking at those reduced costs that we've already produced. Okay, and then step three is the step size, which is the min ratio test. We already have produced this delta X. We're looking at any of those negative. If they are, let me form this ratio. So that's just a, at most ON work, likely much less, because there's usually many fewer elements that are actually negative in that. And then step four, iterate, get to the next thing. This is a vector, a scalar, a vector. So this is just vector addition. So this is a ON work right here. So most things are ON, except, let's come back to this, computing the simplex direction. What's involved to get that? Remember now, this was box 3.5. To maintain feasibility, we just need to solve this system, A delta X equals 0. That's going to be a linear system, a homogeneous linear system, right? Where A is n by n, delta X is n by 1. So that's the most significant amount of work. Think about that, because hopefully you remember from your linear algebra, solving a linear system. So solving A delta X equals 0, n by n, n by 1, n by 1 vector, homogeneous linear system. This linear system can be solved many ways. You learned things like Gaussian elimination, which is ON cubed, LU factorization, inverse, getting inverse ON cubed. This is like ON cubed over 3 maybe, but still big O, ON cubed, right? So those fractions don't necessarily matter. And that inverse only exists for the basis matrix B pulled out from this, right? Because we're only taking an m by m submatrix out of A. That again, we're going to start calling B now. Okay, but we can actually do a little bit better here. So let me write up some more stuff on the board and we'll talk about it. Okay, so in solving this system, so you can solve the whole system, but hopefully when you do several of those by hand, you noticed a couple of trends that you can exploit. And this is the fact that for the leaving non-basic, you're forcing that thing to go in that direction. So you're forcing it to have value 1. And for all other non-basics, remember the non-basic is going to become a basic. That's why it goes up to 1. All the other non-basics aren't going to change. So you're going to stay at 0 for those. So you really just have to solve, these are fixed, you know these. You just have to solve for the remaining basics in that delta vector. And we're going to put those in a vector called delta X sub B. And that sub B stands for the basic variables. So you get the indices of the basic variables, and you're just going to pull those off and put them in their own subvector, delta XB. And then you're just going to pull off the columns of A. We don't need all of A. We just need the columns of A that correspond to the basic variables. That's going to be an m by m matrix because there are m variables, m constraints. And so we're going to call this B. Again, this corresponds to the basic variables. And then because this delta xi equals 1, really, when you've done this by hand, you see that actually gets shifted to the other side. There's a constant that comes over. In a compact way of writing that is negative AI, where this is the column of A, the one column of A corresponding to the leaving non-basic. The one that's no longer going to be non-basic is actually going to be bumped up and be basic and probably have a non-negative value. So this is a vector, a matrix times a vector equal a vector. And so we end by 1. Solving this system, well, it's a smaller system, so it saves us some work. You can do it with the inverse, like in MATLAB, you could just say something like delta xb equals, let's see, multiply inverse on this side, inverse of b, that does the inverse times, and whatever you call this one, negative a, you get that column. Let's see, that'd be all. Let me make some space so you can actually see this. Write it in another. So your code might look something like this. Delta xb equals inverse of b. So you're going ahead and letting MATLAB do that. Or maybe you computed inverse of b up here and saved it and stored it, however you like to code. Times, we want the ith, a negative, we will put that negative up front. We want the ith column, so we take all rows, ith column of A, right? And suppress output if you put the semicolon. All right, and that's gonna be faster than solving this, save a little bit of work. That's the first place where we can do the revised simplex, but there's more savings. Let's make some space. Okay, we can save even more work with this. If we notice that when we actually solve the simplex in the beginning, we need to get an initial basic feasible solution for your MATLAB code for the AX less than equal to B that you're looking at. Your initial basic feasible solution is easy. You're going to add a bunch of, think of as adding plus a vector y of slacks in there, and then you're going to use those as the basis. So we really have an easy basis. And we're going to get, and this is true in general, you're solving, pull off the columns of A that correspond to the basic variables, put them in a matrix called B, and you're solving this. B, xb equals the right-hand side B. Now, the next time, though, so that's just to get the initial basic feasible solution. The next time you're trying to get a simplex direction, and you're trying to get a simplex direction for every non-basic leaving variable I. And you have multiple ones that could leave the basis. If there were 3 non-basics, you have 3 choices that could leave the non-basis and go into the basis. So in this case, there would be I equals 1, 2, or 3. So the right-hand side is changing, pulling out different columns of A, but the matrix is the same. And so when we're solving, when we're going from this to this, the coefficient matrix is the same. It's just the right-hand side is changing. And then for every changes from here to here, and then from A1 to A2 to A3, and so on. And so because the right-hand side is changing, but the coefficient matrix is the same, you can have a little bit of savings. You can compute to solve this, to solve this, to solve the next one, right? There's a V delta XB equals minus A2. There's a V delta XB equal minus A3. Those are the non-basics. Right, 4 systems, but the B is the same. So why don't I just get the B inverse once, or maybe I did an LU decomposition to solve it. Go ahead and save that, and then use it successively. So how much work to do a matrix inverse? O(n) cubed. You do that once rather than here and here and here and here again. We don't need to repeat the work we've already done. We save it, and then to get to solve, say this one here, we have delta xb equals inverse of b, which we've already saved somewhere, times negative ai, right? This is now a matrix that we've saved times a vector. So matrix vector multiplication, that's O(n) squared work. So we went from thinking we had O(n) cubed, O(n) cubed, O(n) cubed, O(n) cubed work to O(n) cubed, O(n) squared, O(n) squared, O(n) squared each time. So great savings there. We can do even better. Make some space. Okay, we can save even more work by noticing this. Now in the next iteration, we're going to form, we had a basics basis matrix, m columns that we've extracted from A, and only one column leaves and one enters. So most of those columns stay the same. In fact, the new B is related to the old B. Only one column changes. And the new B can be written this way. New B is the old B plus something called a rank 1 update. Rank 1 updates are really important in linear algebra and algorithm work on linear algebra. You might not have heard of this in a linear algebra class, but when you take a C as a column vector times a row vector, sometimes this is called an outer product. Two vectors are multiplied and they actually create a matrix, right? This is n by 1 by 1 by n makes an n by n matrix, but it only has rank 1. You can prove that when you do an outer product of two vectors, you get a matrix, but that matrix always has rank 1. Well, rank 1 is super helpful. It's come across often in my work. It's often in updates for search engines, how they analyze things over time. Maybe a query changes just slightly or their database changes and you need to update it. And rank 1 updates are just, you see them, you get super excited, they're magical. They're going to have amazing savings for us. So let's first understand how the new B and the old B are related. So let's say we had this example where this was a basis, a 3 by 3 matrix, 3 columns, and the new basis looks a whole lot like it. The only thing that changes, this one leaves and this one comes in. So the first 2 columns remain the same. And again, that's always going to happen. We notice that up here that the new B and old B, only one column changes. But how can we write that as a rank 1 update? Well, it turns out that this column and this column, let's call it C3 and C3 tilde for the update. You see that a lot in linear algebra. When something is perturbed or changed, you put the tilde on top. Okay, and then we're going to create a vector, column vector C. That's the same thing up here in this rank 1 update. And it's just the difference of those 2 vectors. So I'm going to do C3 tilde minus C3. So the new one minus the old one. And I get this vector here. And then we're going to make a D row vector right here, D transpose. And that is just the third. E3 stands for a vector where it's all zeros except for in the third component, there's a 1. So you can think of this also as either a row or a column of the identity matrix. So you see E's a lot. EI in general stands for the ith column or row of the identity matrix. So we're doing a row vector, so we'll make it a row here. When I do that, so just to practice here, our multiplication with the outer product, C D transpose then is this vector minus 3, 1, minus 1 times this vector 0, 0, 1. It results in this matrix. Minus 3 times this row will be 0, 0, minus 3. 1 times this row will be 0, 0, 1, and 0, 0, minus 1. Now, when I take that and add it to the old B, so I'm adding these 2 matrices here. First 2 columns stay the same. Yep. And then the next ones, I'm adding a 3 and a negative 3 gives me a 0. A 0 and a 1 gives me a 1 and a negative 1, and there we go. Okay, so really at this point, you're just believing something that I said, that this is the case, that these, it always follows this rule here. And now I need to show you why rank 1 updates matter. So we've recognized this, that we've now written it as a rank 1 update. Let's see what we can do with the fact that it is just a rank 1 update. Need some more board space. Okay, here's what's so cool about the matrix inversion for a rank 1 update. And we're going to use this formula called the Sherman-Morrison-Woodbury inversion formula, SMW. Advanced linear algebra topic. Not all linear algebra books have it in here, but this is super helpful for us with the simplex. So bell and whistle that you could put in your simplex code, not required, but know that this exists and what's happening with production code. So if I want to take the inverse of a rank 1 updated matrix, like we did, except we had B before, B plus CD transpose. If I want to take that inverse, it actually can be written as the inverse of A So maybe I already had that from prior computation. I can use that savings. And then I'm just going to subtract out this. And this looks kind of messy, but the denominator is really just a scalar plus a n by n, n by 1 by n. So 1 by 1 plus 1, so a scalar here. And then in the numerator, you can think of this as matrix vector multiplication, vector matrix multiplication. So on squared over scalar. So it turns out that you've got quite a bit of savings, because in general, if you didn't know there's a rank 1 update, and you computed a b at one iteration and then the next b, and you didn't recognize it's a rank 1 update, you're doing on cubed work each time, right? But when we recognize that actually from one iteration to the next, only one column of b is changing. So it's really a rank 1 change to the matrix, a rank 1 update. And because we know the b from the prior iteration, we don't need to compute it again. We can actually use this formula, and the rank 1 updated matrix, its inverse, already gotten. We did one-time work, on cubed work to get that. And then we just do on squared work for this update. We'd much rather do matrix vector or vector matrix multiplication than inversion. So again, we take that, what this simplifies to us for the simplex is you should never do on squared work, on cubed work at every iteration. You should only do it once at most. And then from then on, you can do on squared work. Okay, so homework problems, I think the last few sections I had gone through quickly, haven't mentioned. So just these 3 problems from the last few sections. We've got one more section in chapter 5.